Hello class, welcome to our lecture on 5.7, integrals resulting in inverse trigonometric functions. What I have presented here is the formulas or the rules for inverse trigonometric functions. If you recall, inverse would be the sine inverse, tan inverse, cosine inverse. So we have three of these shared here. We have the integral of du over square root of a squared minus u squared. If you had a setup like this, the resulting answer would be an inverse sine function. Okay, so and then if it is a squared plus u squared, it's a tan inverse u times u squared minus a squared. It's a little more extra terms, but it's a secant inverse expression. Just to kind of highlight the beauty of the derivation, I just want to do the derivation for the first one, just to show you that, how did we get something so complex, an expression, but from a simple logic, from a simple point of utilizing trigonometry and previous knowledge of implicit differentiation to produce this, crisp answer. So for the proof, this is for the first one, okay? We first start by assuming that y equals sine inverse of x over a. Okay, this is our premise. We start with this, and this is just a definition of how you want your y to be. So we got that. Now this only means that sine y is x over a, and a sine y equals x. So I've given you a way to, we started with defining what y is to be, and then we solved it for x. So x equals a sine y. Now we're going to use this to take implicit differentiation, okay? So I will just put that here, and I will say applying implicit differentiation. If you recall implicit differentiation, it is utilized when we have expressions, that have x and y mixed up. It's also used to identify and separate or isolate dy over dx as a result of doing the implicit differentiation. Okay, so here it's this one is kind of straightforward because the right side is dx over dx, which is basically 1, and the left side has only one variable, y. Implicit differentiation is very powerful to use when you have, let's say you had sine xy or something like that. So if you had x and y mixed together, then it helps us to use product rule and this rule and that rule to separate them out. But here it's pretty straightforward, so we just can go ahead with a, which is constant, pulled out, and the derivative of sine y, derivative of sine y with respect to x would then require chain rule because of implicit differentiation. So derivative of sine y is cosine y times, that's the derivative of the outside, times the derivative of the inside. The inside is the y, because y is not x. The resulting derivative of y would be dy over dx, and the right side will be 1. Okay, so the left side involved chain rule as part of the implicit differentiation. And implicit differentiation expects us to solve for dy over dx, which is going to be 1 over a cosine y. So we got 1 over a cosine y. Now we're going to use, I told you how we will be utilizing trigonometry and previous knowledge or previous understanding of calculus to help us to go back and forth to build this out. So along those lines, we are now going to use Pythagorean identity from trigonometry, which says sine squared, because we have a y, we'll just use y. Sine squared y plus cosine squared y is 1, isn't it? So from this, you can solve for cosine y because that's what we need to substitute. So cosine y will be square root of 1 minus sine squared y, isn't it? You first subtract the sine squared y and then you take the square root. Usually it'll be a plus or minus there, right? But, our y here will be between negative pi over 2 to pi over 2, which implies cosine y will be positive. So we only choose the positive option for cosine y. Okay, a little bit of rigor there because we need to make sure that we are utilizing, we can't just forget about the plus or minus option because it's a square root, but we are able to choose the positive side of it because of the domain of y. Okay. Why is that y coming? Because that is the reason why we started off with y as sine inverse, right? So that is what helps us to get a domain for y that will remain positive. So if it helps, we can actually bring that here. Okay. All right. So then we come back here, and then I have 1 over a times square root of 1 minus sine squared y, as I just mentioned. We're utilizing the positive square root. Okay. And then now we use algebra to kind of manipulate this. The algebra we use here is this a can be written as square root of a squared, isn't it? And so that is 1 minus sine squared y. And then that can be brought together under 1 square root, which is a squared times 1 minus sine squared y. All this is algebraic manipulation. So that gives us square root of a squared minus a squared sine squared y. But then if you go back up a little bit as to our original assumption, we got, I kind of use that in a step, but from here, maybe I will just write it out here. From here we got x equals a sine y, isn't it? That's the step here, to which I applied the derivative on both sides. But we got x equals a sine y. So we're going to use that information here. X equals a sine y. So x squared will be a squared sine squared y. And I can insert that in here as 1 over square root of a squared minus x squared. Okay. And what was on the left side was dy over dx. dy over dx. Now remember, we're trying to find the antiderivative, right? So this is dy over dx when we chose y to be sine inverse of x over a. Okay. The one caution is because of all this, we just throw in an absolute value of a in the formula. So this is basically what our formula is saying. Our formula is saying, well, if the derivative is this when y is this, then if you're trying to write this in terms of integral, right, the integral of we're using x here, right? So I'll just say dx over square root of a squared minus x squared will give back a sine inverse of x over a plus c. But we throw in the absolute value of around a to make sure that that remains defined when you go in the opposite direction, right? So when you went from y to dy over dx, it was okay because we were able to define the conditions for y. But when we are trying to rewrite this formula in the reverse order by using the integration of the derivative, then we are bringing in the absolute value of a. So anyways, I hope it gives us an appreciation for how these kind of complex formulas are derived from existing knowledge that was built through algebra, through trigonometry, and through the earlier levels of calculus. Here we are asked to evaluate a definite integral, 0 to half, dx over square root of 1 minus x squared. Okay, so we have this format resembling the formula which had dx over square root of a squared minus x squared. Let me see if we can quickly reference the formula here. Okay, so we have integral du over square root of a squared minus x squared. In this case, they're using u, but I'm just calling it x. Sine inverse of u over absolute value of a plus c. That's the same thing that we just derived. So let me come down here. So that's going to be sine inverse of x over absolute value of a plus c. Right. So now our a here is, in this current problem, our a here is 1. Okay. So let me just write that down here. Integral 0 to half dx over square root of 1 minus x squared will be sine inverse of x over, just for emphasis, I'm putting in as, okay, it's not 111, it is, I'll exaggerate that, the absolute value bars, so you know, I just substituted this. There is a plus c, but that was for the indefinite integral, because this is a definite integral, again to avoid confusion with the absolute value and all that. I am putting it as a bracket. So that is direct application. Now with simplification, this will simply be sine inverse of x. And I can use the bar now because we don't have the absolute value bars now. So this is the vertical bar should do. And that will be sine inverse of half minus sine inverse of 0. Sine inverse of half, so you go back to your unit circle and you're trying to see what is the angle for which the coordinate, in this case the y coordinate is half, right? What's the angle for which the y coordinate is half? The angle will be pi over 6. And same question here. What is the angle for which sine inverse, sine inverse is 0? That will be 0, right? The y coordinate will be 0. So the answer comes out to be pi over 6. So here's our problem where we evaluate an indefinite integral, dx over square root of 4 minus 9x squared dx. Okay. To quickly recall, this resembles, once again, integral dx over square root of a squared minus x squared dx. The catch, though, is it's not just an x squared, it's got a 9x squared, right? So then we have to, once again, take it into this format. So you want something squared minus something squared to make it resemble this format. So that's going to be 2 squared and 3x. Still, it's 3x, not just a plain x, for us to directly apply the rule. And so we have to use the substitution method. Okay, please remember, don't take it lightly that, you know, you've got the format resembling very close. The format works only if it is an exact x that you can directly substitute for the answer as sine inverse of something. So to get there, we have to use the substitution method. So let u be equal to 3x. So du is 3dx. There's only a dx on the top, so we have to divide out by 3. So integral dx over square root of 2 squared minus 3x the whole squared will now be du over 3, right? And then there is square root of 2 squared minus u squared. Do we see that? So we have a way to substitute that. Now, because the 3 is a constant and 3 is happening in the bottom, remember to pull it out as 1 over 3 du over square root of, you can write it as 4, but I'd like to keep it as 2 squared minus u squared, only because that is the way it resembles this format. So I can see the A very clearly to be 2. Okay, otherwise, we'll incorrectly might mark it as 4. All right, so that's going to be 1 over 3 times sine inverse of x over absolute value of 2 plus c. Here it's okay to do the plus c because it's an indefinite integral. I just made a mistake. I wrote x using the letter u, right? So it should be u over absolute value of 2. So that's going to be 1 over 3 sine inverse of u was 3x. And absolute value of 2 is 2, so 3x over 2 plus c. And that will be our final answer for this problem. Our next problem is evaluate integral 1 over 1 plus 4x squared dx. Notice how it is, there's no square root in the bottom, and it is a plus 1 plus 4x squared. So do we have a matching formula for this? So let's go back. Yes, in fact, the second one is the only one without a square root and with a plus, and that is to do with the inverse tan, right? Tan inverse. So we can use this formula. It's got that 1 over a expression, and coefficient in front of tan inverse of u over a plus c. So come down here and utilize that. Oops. So let's write the formula by the side. So that's integral du over a squared plus u squared, which is 1 over a tan inverse of x over a plus c. So we will rewrite this to resemble that format. So 1 is the same as 1 squared. We're just trying to resemble this, right? So I'm putting it as 1 squared, even though it may appear redundant. And this would be 2x the whole squared, right? So your u is actually the 2x. So then we have to then do that substitution because it's not a plain x. I made a mistake here, I just realized. If it is x, everything has to be x, right? So I have an x here. So this will be easy for us to compare. So is it an actual exact x? No, it has got a 2x. So this one must be, let u be equal to 2x. Du is 2 dx, which implies du over 2 is dx. All right. So let me finish this up. So that's a dx on the top. So that will be du over 2 times, then you have this 1 squared plus u squared, right? Okay, so that's going to be a half pulled out, du over 1 squared plus u squared, which implies I have a half times, the formula is 1 over a here is 1, so 1 over 1. I'm writing all this to explicitly show that we are substituting it directly. So that's going to be u over a, x over a, so that's u over 1 plus c. Okay, so that's going to be half tan inverse of u plus c, which is half tan inverse of 2x, because x is 2x, plus c, and that will be our answer. How about this? Evaluate integral 1 over 9 plus x squared dx. This is again a fun problem because we don't need to use substitution method because there is a direct x there and everything is matching up nicely. So you can directly go into the answer, which is 1 over a is 3, 1 over 3 tan inverse of x over a, so that's x right there, over a, which is 3, plus c. And that's it. So it is a one-step answer when your steps are, or when your expression lines up nicely with the formula. Here comes our last problem. Evaluate the integral of root 3 over 3 to root 3 dx over 1 plus x squared. Okay. So this is a definite integral, and we look at the format. The format resembles the tan inverse, and the x is exact x. So we can directly get to the answer, which is 1 over a. A here is 1. Tan inverse of x over a. X is the variable here, so x over a, which is 1, plus c is what we do, but then we have the definite integral, so I will just write it as root 3 over 3 in the bottom, root 3 on the top. Clean that up, we get tan inverse of x, root 3 over 3 to root 3, the limits. Then apply the upper limit minus the lower limit. Okay, to evaluate this, you have to go to the unit circle. It's tan inverse, right? So you're thinking of finding which angle will give me root 3 and which angle will give me root 3 over 3. Because it's tan, it's got to be sine over cosine, so you're looking for the y coordinate over the x coordinate. So when you look at the unit circle, we notice that for the angle pi over 3, the coordinates, right, the x and the y coordinate, that will be half comma root 3 over 2. So if you, and this is, this is cosine and this is sine. So because it's tan, it's going to be sine over cosine. So root 3 over 2 over 1 over 2, which is root 3, right? So for root 3, tan inverse of root 3 comes out to be pi over 3 minus. And we also see that for pi over 6, because we want to do the flip of that, right? Root 3 over 3. The flip of that will be, we have root 3 over 2, comma 1 over 2. So if you did sine over cosine, that's going to be half over root 3 over 2, which is going to be 1 over root 3. Okay? But then if you rationalize the denominator, 1 over root 3 times root 3 on the bottom times root 3 on the top, that's going to give us root 3 over 3. So for root 3 over 3, the tan inverse of root 3 over 3, the angle is pi over 6. Okay, then you take the LCD, so it's 2 pi minus pi, which is pi over 6. So the answer for this comes from, obviously, an extensive use of unit circle, and the key within the unit circle is to remember to do sine over cosine, which is the y coordinate over the x coordinate. And additionally, for the second part, we had to do rationalizing the denominator, because the 1 over root 3 is not what is presented here. It's root 3 over 3. So we have to actually manipulate it through rationalizing and getting the root 3 over 3 format. Okay. I hope that was helpful. That concludes our lecture. Thank you very much.